Now the conclusion part. We find the solution. The solution for the n-disk problem. All right. Then we can write this pseudocode. The final version of the pseudocode. So simple. Just a few lines. So we write this recursive function. Move disks with 4 parameters. The first parameter, the number of disks. Then the remaining 3 parameters corresponding to 3 pegs. Peg 1, actually the order here should be the peg 1, peg 3, because destination 1 is the third one, then peg 2. In that order. All right. Then, when we call this function recursively, you need to be very careful. For other parameters, okay, but you need to fix the order of the pegs for these 2 calls. Peg 1 and peg 2, peg 3. So this, all right. Why? The writing, some problem here. All right. This is the destination. In the first recursive function call, you make a peg 2 your destination peg. The last one, peg 2 as your starting peg. Oh, my pen looks not quite right. Right. So 2, the destination. Yeah. So my pen, it's very strange. Well, cannot write smoothly. 2, 3. Oh, I need to change a pen. Yeah. Very strange. Let me change a pen. Change a different pen. All right. 3 and 1. 2. All right. Yeah. In the middle, so here I used C++ syntax. Because this problem I picked from data structure. I taught that data structure 2250 before. So I took from there. All right. So here you can see the main reason I select this problem is I want to show the power of recursion. Now you can solve the n-disk problem. We know it's not easy, right? Pretty challenging. N-disk problem with just these a few lines. You can get a solution. Only just small number of lines. Think about, without using the recursion, how can you solve this problem? Extremely hard. That's the big power you can experience in this recursive algorithms. That's the reason people use recursive algorithms in problem solving. It has a big drawback because the resource consumption pretty big. The stack, the deep stack problem, always there for recursive algorithms. But people still are willing to pay that much resource to get a very powerful solution. But you need to know the bottleneck. The bottleneck is that deep stack problem, potential problem. Memory consumption sometimes could be very big, memory consumption. Yeah. So that could cause some problem in your solutions, in your real world applications. So in that situation, you need to think about a technical solution to reduce the depth of stack. Can you find a way to reduce the depth of stack? Think about that question. Reduce. Yeah. Here, let me raise the question. Later, when I have a chance, I can talk about the ideas for the solution. Yeah. Let me raise this question here. How to reduce the depth of the stack in implementation of recursions. This question, okay? Yeah, because otherwise, you may not be able to complete your solutions. Yeah. Even if you find a perfect solution, but due to this resource, because this is a resource problem. Nothing to do with your algorithm, right? Yeah. So your algorithm has no logic problem. Your algorithm works in some perfect way, but this bottleneck may cause some problem. Okay? Yeah. All right. So we complete part A. Now let's move to part B. Let me switch PowerPoint slides to part B. Oh, actually, I do not need to switch because I put part B after this part A. Yeah. So let's go to the next slide. Yeah. Part B. Yeah. All right. Yeah, I put together, so I do not need to switch. All right. The topic title, variable size reduction. Remember part A, basically what we did, size 1 reduction, right? Yeah. So that's the simplest case. So size 1 reduction. And here we will see other variations, variable size reduction. All right. B.1, reduce the problem size by half. Every time when we do divide and conquer, we split the original problem right in the middle. And we only need to solve one of the 2 subproblems. We do not need to solve the whole problem. In that situation, we divide the problem size by half. We throw away the other half. We only solve one of the 2 subproblems. That's the case. Reduce problem size by half. All right. Problem number 9. Count binary digits. Yeah. All right. Yeah. So another simple computing problem, but you can see one variation for problem size reduction. Given positive decimal integer, here we emphasize decimal, because later you will see that we will use the binary numeral system. In this question, we consider two numeral systems, decimal numeral system and a binary numeral system. All right. Find the number of binary digits, bits, right? So binary digits, so we call it bits, in its binary representations. Pretty straightforward. So you know how to do the conversion, right? But here we need to count that number of bits. All right. Here we apply recursion. First, let's look at the representation part, because two different numeral systems. When we do the conversion, we need a mathematical representation. All right. How to represent a decimal number in binary format? This is the standard way. All right. Left-hand side, decimal number, and the right-hand side, so we use base 2 representation. Here, look at the base number. Base number binary, so the base number is 2. So we use the base 2 representation. All right. The first term, B0 times 2 to the 0. 2 to the 0 equals 1. Yeah. So that's the reason you do not see base 2 here. Yeah. But there is a hidden base 2 there. Yeah. Then, for other terms, you can see the pattern. The coefficient number B0, 1, 2, 3, all those coefficients, you only take the value 0 or 1, right? Yeah, 0, yeah, all the bits, yeah, all the coefficients, they are bits. Bits we know, 0 or 1. Only two values, 0, 1 for the bits. Okay, all right. But the last bit, or we call the most significant bit, must be non-zero. Otherwise, if it is 0, we throw it away. We do not need that term. We just move to the next non-zero bit. So here we assume B sub s not equal to 0. All right. Then it can only be 1, yeah, because 0 or 1. Yeah. All right. Then the answer, because when you count the number of bits, now here we can see all those bit numbers, right? The number is s plus 1. All right. So we have the answer, we have the representation of the answer, but in our representation, we use a different variable, s. Different variable, s. But our input data, we only have one input data number, that's n. We're not given s. We're not given s. Yeah. So your answer should be in terms of n. Your answer expression should be in terms of n, not in terms of s. So you need another step. You need n expression to replace s. The value-wise, you need the same value, s value. But you want to use n representation to replace s value. All right. But how to get s? All right. So here we need to find a way to calculate. So here our goal is we want to calculate this S. When we calculate S, we want to use N, the input number. Input is N, the output is S. Yeah. N is known, S is unknown. So we need to do the calculation to get S. All right. Then we want to find a recurrence relation to get S. Yeah. Recurrence relation to get S. Yeah. All right. Use transformation to change the structure. Because this formula, this is our main formula to work. Yeah. So that's our, source, right? Valuable source. We can do our work. So we are going to do transformation. We manipulate this formula. All right. What kind of manipulation? So the manipulation you want to do based on the structure. What is the structure here? Look at the typical structure in the given expression. The structure, you can see a lot of power of 2 expressions. Power of 2 expressions. So you should take advantage of the special structure of power of 2 numbers. How to take advantage of that structure. Power of 2, special structure. Division by 2. Division by 2. Integer division by 2. Yeah. Why integer division by 2? Because when you take integer division by 2, a power of 2 number, on a power of 2 number, you still get power of 2, right? Yeah. Yeah. So you maintain the power of 2 structure. You do not break it. You change it, right? You change it, but you still maintain the typical structure there, right? Yeah. Yeah. So that's the reason. Yeah. So we should choose appropriate operation to do the manipulation without breaking the structure. That means after our operation, we still maintain the typical structure of the original formula. So that operation is integer division by 2. All right, so let's do it. Let's apply the division. Yeah. Left-hand side, because it's integer division, so you drop the fractional part. If you have a fractional part, you drop it. Okay? So you only keep the integer part, so that's n over 2. Then you take floor function. The right-hand side, the possible fractional part only comes from the first term, right? Yeah. B0 could be 1. When the B0 equals 1, that corresponds to the fractional part. For other terms, no fractional terms. Other than the first term, for all the other terms, no fractional part. Yeah. So that's why after division by 2, nothing comes from the first term. Nothing. But for the remaining terms, you can see you have an easy way to division by 2. All right. So then you get a different formula, you get a new formula, but this new formula still maintains the typical structure of the original formula. How about that? All right? Yeah. So this kind of transformation is helpful. This kind of transformation is helpful. All right? Yeah. So now we apply our recursion view. Recursion view here on these two formulas. Okay? All right. The first formula, we get a binary representation for n number. The second formula, we get a binary representation for n over 2 floor function. Binary representation. All right? Yeah. But they are correlated. Here you can see these two subproblems. Yeah. So you can see subproblem 1. So this is subproblem 1. Then subproblem 2. Okay? Now we want to, there is a gap, right? Yeah. There is a gap between these two subproblems. Now we want to find a recursive formula to connect these two subproblems. Yeah. All right. Yeah. So that's the basic thinking. Yeah. All right. Yeah. Observation. Yeah. The least significant bit is removed. Yeah. B0. That's the least significant removed when we do transformation. All right. After that, the number of bits is reduced by 1, right? When you count the number of, here you can see all the other bits remain, right? You remove the first least significant first bit. Then all the other bits remain. You still keep. So the difference is 1. Before transformation and after transformation, when you count the number of bits of the binary representations, the difference is only 1. That observation is important. Okay? So that observation is useful when we discover the recursive formula. And the problem size, when you look at the problem size is reduced by half. Look at the problem size here. Approximately n over 2. Although not exactly, but it's a good approximation. Very close approximation. So we call it half size reduction. Half size reduction. All right? Yeah. Then the recursive formula, if we use a function, binary recursion, just some name, appropriate name. There, parameter n, original problem size n, it relies on the solution of half size subproblem. Floor function of n over 2. Approximately half of the original problem size, but still the same problem, so we call the same recursive function, and the difference is 1, so we add with that difference 1. That's our main recursive formula here. Okay? So if you can solve this recursive equation, recurrence equation, then you get a final solution. So our next question, we want to solve this recurrence equation. All right. It has a base case. Yeah, base case. So where the data size is 1, your bit number is 1. 1. Your n equals 1. So you count the number of bits, also 1. Yeah. So that's the base case. Then we have a complete equation. If you do not have the base case, then you cannot solve a solution. So this is our starting point. So we have a starting point to start our recursion, right? Yeah. Growing up, yeah, here. So this base case allows us to grow the problem sizes. Yeah. All right. Yeah. Otherwise, your recursion is baseless, right? No base is baseless. You can not get anywhere. So the base case is important. All right, now the solution. In computer science, when we do division by 2, yeah, because we know computer use the binary system, right? Yeah. Inside computer implementation, the most convenient way is the binary representation. Yeah. Because only 2 signal, 0, 1 representation, good enough. You can represent everything. So the most friendly representation inside computers. Yeah. All right. Then when we do division by 2, so the CPU does not really need to do the regular division. Because the regular division, it is very complicated. But division by 2, it's very easy. It is just a left shift operation. You shift the binary point. Because you have integer part, fractional part, you need one binary point to separate integer part and the fractional part. So when you do division by 2, you just shift that binary point 1 position to the left. All right? And when you only keep the integer part, you drop the fractional part. That shift operation inside CPU is extremely fast. So that's why. So why people talk about shift operation? Because it is extremely fast. How fast? How fast? Is the shift operation. Let me give you some idea. All right. Let me give you approximate idea. Yeah. To see how fast it is. Yeah. So basically faster than an integer addition. Faster than integer addition. How fast it is. We know integer addition in CPU already very fast, right? Yeah, already very fast. Because integer multiplication much slower than integer addition, 10 times slower. And integer division is 40 times slower than one integer. Integer, if you do one integer, so division by 2 is an integer addition. If you do regular division, comparing with integer addition, 40 times slower. That's how slow it is. All right. Let me use some simple numbers to give you some idea. Okay. Yeah. So INT addition in CPU approximately 2 nanoseconds. Okay, not exact, approximately 2 nanoseconds. Yeah, all right. Then integer multiplication 10 times 20 nanoseconds. Okay, all right. Then integer division 40 times addition, right? So that's 80 nanoseconds. How slow it is. All right. Now, shift operation. Faster than addition, 1 nanosecond. That's why people use shift operation, right? If you compare with regular division, 80 nanosecond versus 1 nanosecond. That's why if you have a chance to use shift operation, you should use the shift operation. Extremely fast. Okay, all right. So now, here, we count the number of addition. Because every time when we change the problem sizes, we do 1 addition. We add 1, right? Yeah. So we count that. Yeah. All right. Define a simpler version of the function a of n as number of additions. Yeah. Add that 1 number of additions. All right. So we have a similar recurrence relation. Yeah. Just a simpler version a of n. Yeah. Yeah. But the meaning is slightly different. The values should be the same. All right. Then I want to look at the solution part, because in the solution part we can learn a lot of problem solving techniques, thinkings. Yeah. All right. Question: how to handle the floor function? Now we need to solve this recurrence relation. But in this recurrence relation, this part is relatively hard to handle. Not very convenient. Floor function of n over 2. Because there are 2 cases we need to consider. When n is even, the floor function has 1 expression. And when n is odd, the floor function has a different expression. So those 2 cases, although not too many cases, but not very convenient to work on. Under this situation, what should we do? Here we think using the typical problem-solving methodology here. Problem-solving. Under this situation, what should we do in general? We did similar things before. Here, I just want to remind you some important problem-solving strategy we did a few times before. When you see something relatively hard, under this situation, when you see something relatively hard, what is the typical way for us? We, as problem solvers, what's the best strategy we should take in this situation? We did that before. Remember, so here, let me remind you, a special term in this situation. Yeah. All right. In last class, is it last class? Yeah. So, So I mentioned one one special name in problem solving called the golden rule. Golden rule of problem solving. So let's recall this rule, and we apply this rule here. So what's that? When you solve a relatively hard problem, one special method you can use it. You can modify the original problem to make it easier, and we work on this easier version first. After we find that solution, then we go back to the original version. Do you still remember that? Yeah? That's the golden rule. You can modify the original problem. Okay? So, if you have the freedom to make that modification, to make the problem much easier, what can we do here? We want to apply this golden rule in this situation, this special case. This special case, this floor function part is not very friendly for us. We feel not very friendly. We want to get rid of this floor function to make it more friendly. But you cannot drop the floor function directly, right? If you drop it, then n over 2 may not be an integer. So then your problem does not make sense. So that modification is not a good one. Not acceptable, that modification. So you should make a valid modification. Not some absurd modification. All right, so here, let's make reasonable, appropriate modification. What should we do? Then, let me remind you another commonly used way in problem solving, another one. We used that before. Yeah. We can make assumptions, remember? Yeah. In many cases, we can make assumptions. Remember? When we sort an array, we can assume all the elements are distinct. Then we work on it. After that, we can remove that assumption. Right? Remember that? So that idea we can also apply here. Here, you can make convenient, friendly assumptions. But later we can remove it. So another important method we should use here. All right. When we make assumption, we target this floor function. We want to improve our situation in this floor function. So what kind of assumption is friendly for floor function? Division by 2. Assume n is even. How about that? We assume n is an even number. Then we can take away the floor function immediately, right? Without any loss. Because n over 2 is an integer. Then when we apply floor function, nothing changes. Nothing is wrong. All right? But we make our assumption. N is even. Is that okay? Is that okay? Based on our previous experience, it is okay. Because that's our first step. Think about when we make assumption. If other people argue with you, how can you do that? You can say, that's our first step. It's not our final step. Our final step, we will target general n, but our initial step, we can work on the simplest case first. All right, so then we can add that even number assumption. All right, here, for the floor function, we know even number n, that's the best case we want to have. The other case, not very convenient. We don't like it. We want to avoid it. All right, so we make that assumption. All right. What do you wish to have? Yeah. So when you ask this question, you always want to have the best case scenario, right? You don't want to have the worst case scenario when you make a wish, right? Yeah. You don't want to give yourselves hard time, right? Yeah. So that's the question. We want to make our life easier. All right. So we wish to have n even here. Okay? All right. All right. Then, that's just first round. When n is even, we can remove the floor function. But how about the next step, right? Because when we do this recursive function call, we need to call it many, many times. The next round, when we call it, we have a new floor function case we need to apply. And n over 4 may not be an integer, so we have some sticky point again. All right? So we want to remove it. The unfriendly part, we want to remove it. So how can we remove it? We make more assumption. We make another assumption. Can we make n over 2 even, or n is a multiple of 4? When n is a multiple of 4, then n over 4 is an integer, right? So here you can see we need to make more assumptions to make our lives easier. Then we keep going, yeah, because we need another function call, right? We need to keep calling this function recursively many, many times. How can we, make our lives easier for the whole process? The best thing we can get is when n is a power of 2, then all the floor functions are gone, right? Yeah, because division by 2, everywhere, no fractional part, all integer part. Then all floor function application would have no change. No change. So we don't need them. We can remove all the floor functions under this big assumption. This is a big assumption, right? It's okay because this is our initial step, all right? Only initial step. So our initial step, we want to work on the best case scenario. This is the best case scenario. All right, then next, let's find a solution. Now, we need to get a solution. So under this best case scenario, what is the final solution? All right. We assume n is a power of 2. All right. Then k is log base 2 of n. Log base 2 of n. That's k. All right. New recurrence relation. Under this big assumption, let us rewrite our original recurrence relation in a new, more friendly format, and in this new format, all the floor functions are gone. Very nice. Yeah. You do not need to deal with any floor function. Yeah. All right. So that is capital A of 2 to the k equals A of 2 to the k minus 1 plus 1. No floor function. And every time you do division by 2, no fractional part. Always integer part. So our first recursive function call, second recursive function call, third one, and so on. Keep doing until we reach the last recursive function call. The last one. Okay? Yeah. Then, all right, let's add up all these equations and do cancellations. By your eye observation, you can see the easy cancellation in this way, right? Yeah. In this pattern. Yeah. So at the end, you can write capital A of 2 to the k equals, can you see this final answer k minus 1? Because you only need to count here the initial value, capital A of 1 equals 1, right? So this number equals 1. So 1. So that's this number. And then you accumulate all the ones from all the equations. Can you count the number of equations? Can you tell me how to count the number of equations here? In this situation, how to count the number of equations? We need to do this. Count the number of equations. Any idea? Yeah. Here, let me recall. We learned this method before. Counting by reference, remember? In Module 1, we learned this technique, counting by reference. How to get a one-to-one correspondence. Each equation, we need to choose an appropriate mathematical object to make a one-to-one correspondence. Here we use subscript, or superscript, not subscript this time. So K superscript corresponds to the first equation. K minus 1 superscript corresponds to the second equation, and so on. The last equation, we use this 1. Superscript 1 corresponds to the last equation. All right. So when you count the number of equations, now you just count your superscripts, right? Your superscripts start from 1, 2, 3, and K, right? So when you count the number here, number in this set, that number equals K, right? So that's why you have this K. So this simple technique. Otherwise, how do you keep track of your data? You have a lot of ellipses here in the middle. How can you keep track of your data? So we use this method to help us keep track of the data. All right. Now, the final conclusion. Yeah. Because you have your solution expression, right? But we need to write it in terms of n. This k is an intermediate variable. It's not original variable. Original variable is n, but our answer is in terms of an intermediate variable k. So we need to go back to the n expression from k expression. So when we get back to the n expression, capital A of n, because 2 to the k equals n. So we replace 2 to the k by n, and we need to replace k by log base 2 of n. Then 1 plus. Yeah. So we get our final answer this time in terms of n, when n is power of 2. When n is power of 2, we have this answer. It's correct. The answer is correct. But the question is, if n is not power of 2, because this is our initial try, right? Our first try. This is our first try. We need to go back to the original question. Our first try is on the best case scenario, and our final solution should be on the general case. Arbitrary positive integer n for our final solution. So next step, how can we move from the best case scenario to the general case? Another big step, jump. Here we need to make another big step jump here. Jump from power of 2 to arbitrary integer, arbitrary positive integer. The difference is big. Okay, all right. Now, our next round problem solving. So that's why I want to use these examples to show you a lot of thinking methods in problem solving. This time we need to apply another round problem solving strategies. All right. Make a guess this time. We need to make a guess. Here I want to emphasize, guessing is very important in problem solving. Make a guess. Make a guess. Many times in your problem solving, you need to make a guess. Okay? Yeah. When you make a guess, you do not have to guess the final solution immediately. Yeah, because nobody can guess the final answer, right? Yeah? Yeah, because the final answer could be very complicated. Nobody can make the correct guess all the time. Yeah. People can make correct guess sometimes, but not all the times. Yeah. All right. But don't worry, still, it is very useful, very important to make the best guess you can make. The best guess you can make. All right, let me leave this important guessing discussion next time, because the strategy here also very important. So next time I want to spend quite some time to discuss this guessing strategy. All right, see you next time.